The Department of Material Science and Engineering is responsible for the curation of the discipline of material science and engineering as we teach it to our students here at MIT. Our entire curriculum is built on hands-on discovery and invention, and in the future what that means is that increasingly we would like to take any element of the educational process that is not hands-on, and we would like to package it and make it completely flexible. In our department, I think we all believe that the future of education will be more efficient than one-to-many delivery of content, right? So the lecture model where one person delivers to hundreds of people, that kind of content can increasingly be made compartmentalized in online modules where students can not only sit one time through a lecture delivered at them, but they can watch it over and over again. It can be hyperlinked to appropriate text materials and reference materials, and it can be available 24 hours a day, 7 days a week.
So for instance, I teach a course on the mechanical behavior of materials, and I've been teaching that for many years here at MIT. I've also developed it as an online course through MITx and edX. So to do that, we videotaped the lectures, I developed screencasts of examples, a little like the Khan Academy. I worked out examples on a tablet so students could see that. We have online problem sets now. And all of these things that I developed for the online outside education for people outside of MIT is also available for the MIT students. The online students outside of MIT have been very enthusiastic, and they've been very appreciative of what MIT has done here. I think people are a little stunned and amazed that MIT is making all this material available and that the quality of what's offered is so good. I've been impressed with how many different countries the students have been from who are taking the online courses. My mechanical behavior of materials class, which was taught last fall, had students from over 140 countries taking it, and I thought that was really remarkable.
One of the things that we love in material science and engineering is that when you've gone to the trouble of designing and constructing a new materials can be used in lots of different ways. And so it's pretty common that we might be designing a material for one application and we find that it's a platform technology and it can be applied broadly across a whole range of industries.
Our lab is interested in manipulating and recording neural activity in both the brain and the spinal cord and also peripheral nerves. And in order to do something like that, you need a device that is flexible so it can address the mechanics and materials properties of the neural tissue. We decided to leverage multi-material fiber technology, which was largely pioneered by Professor Joel Fink, also in our department, except that we decided that we needed to use really soft materials that are, most of them are polymers and polymer composites. And then we can introduce all of these materials into a structure which is a template of the device, and we can now implant it into the brain or the spinal cord or peripheral nerves and interact with that complex system minimally invasively. We're extremely excited what we were able to do with this technology, with this type of materials processing, because before we came into the field of neural engineering, there was really no way of creating those complex multifunctional structures. And what multi-material fiber technology allowed us to do is to incorporate all of those different modalities into a structure that is still very sleek and very biocompatible.
Energy research in general offers tremendous opportunities for material scientists and engineers such as myself. Right now, one of the things that really fascinates me is whether or not we can get the cost of energy storage down so low that we can have a technology that enables not just the hourly shifting of something such as solar energy, not even daily, weekly, but actually seasonal shifting. So that, for instance, in the Northern Hemisphere, where we have so much more sunlight in the summer than in the winter, it would be possible to store energy seasonally, store it in the summer, and actually use it again in the winter. That will require new battery technology of extraordinarily low cost and high performance.
SMART is MIT's research lab in Singapore. It is designed to be a new experiment in international collaboration in areas of research that interest both Singapore researchers and MIT researchers. So an example of what we're doing is shown here. This is a 200 millimeter silicon CMOS wafer, but it's actually quite unique in that we have the ability to peel off state-of-the-art silicon circuits supplied by a real manufacturing environment and put them onto engineered substrates. allowing us to integrate new kinds of materials and devices into integrated circuits for the first time. That's the kind of thing that our collaboration in Singapore allows us to do.
A new consortium, which is a mega consortium, which is called AIM Photonics, is part of a set of manufacturing innovation initiatives that the Obama administration has installed. And AIM Photonics is the fourth commissioned one, and now there are 7 that exist. And the role of AIM Photonics is to combine manufacturing facilities where industry can participate in design, developing processes, and developing new concepts, and produce those prototypes in a foundry type operation.
It's an exciting time for materials science at MIT. The faculty has grown by 1/3 in the past 5 years, and we right now are watching the construction of a new materials-centric building right at the heart of campus. In the end, if we get more students in the lab, working on hands-on discovery and invention, the world can be a much better place.